Yes, the live is starting now. So let's get back here. Okay, hi, hi everyone. Now, would you give me some feedbacks from what you have in the last two sessions? We have some discussion about optimization. We ask some question both for a single optimization problem that you were supposed to define a penalty function in the session on our first day. And in the second session, we asked some question about form in optimization and how we can handle form. I guess in policy, I want to say, I want to know what you think about it. Did you found any solution or any special tricks you have to deal with form while you're running an optimization? Okay.
Well, for about the form on the second section on the first day, I thought about it that the way I would do it, it would solve it with the parameter itself. Instead of has them both freely adjustable, I would probably have one slider would be always be greater than another one to keep the form consistent. That's the way I would do it.
That's good. That's actually one of the best tips that we can do. So as Mai said, he said that he will review the how he defined the problem, how we defined the problem, and in that problem definition, he will adjust the number slider or the way that form develop or generated in a way that we do not have repeated form with the same performance. Yes, that's what you said.
Yes, thank you for the elaborating.
Yes, exactly. That's one of the best things. That's one of the things that I want to pay your attention to, that how important it is to pay attention to the way that you define your optimization problem. There are, of course, other tips and tricks for doing that, but the bad news is that yes, algorithms, especially optimization algorithms, do not care about your form, do not care about your design. They care about numbers and digits. So if you think that you want to design something and you care about the form evolution during your optimization process, even when you go advanced and work with machine learning algorithms, when you want to do like run a neural networking algorithms, in those algorithms of the same thing is happening. You should care about the form yourself rather than just give the algorithm all the responsibility of this. Will you please beg me for a minute? Beg me.
Please turn on the mic.
Yeah.
Yes, thank you. Thank you. So, yes, Luca, I will share a sample of sheets in InDesign. Yes. Hi, Super. I will share that with you, and thank you for reminding me. I will upload the sample for your final project in the Google Drive, and I will notify you in the group. Thank you. Okay. Here in the day one optimization theory, if you remember what we had here, yes. So in this particular problem, we define a very simple optimization problem, and we ask you to know, we ask you if you can solve the last one. The last one was uh, the last one was something that we ask you to add a penalty function. This is from the morning session, and there we go. Yes. And here. Okay, if you remember, we add an obstacle here. We add something like this, and we ask you to consider this as an obstacle and redefine the algorithm in a way that the solutions avoid this obstacle. Like if the table sits here, if anyone want to go from this table to this machine, he will just trap in the obstacle. Like this is what we don't want to happen. So we want our table to sit in this area. Yes, this. From this area, these are where our table can be. But here again, you see we have a brush here with this obstacle. So let's get here. So these are the allowed area, and these are which are not. One of you, of course, send a good solution for me. I just want to run my own solution too. Let's see what we can do. Uh, the best way to solve such a problem when we have an obstacle, when we have something that we want to avoid from all of our solutions, it's to screen what's happening during the optimization and tell our algorithm or learn our algorithm in like in a machine learning algorithm. We need to train our algorithm how to avoid that obstacle. I know there are so many ways that we can just delete the options that we don't want. Like I can say, okay, instead of searching the whole surface, easier to write in here. So I can say if this is the whole area that I'm going to search for a point for my table, and this is the obstacle, instead of searching the whole area, I will find some area that is available for me, like from here to here, and then run an optimization on this area. Yes. While this can be a solution, this can result in something that we want, but this is not what we exactly expected because this is so super simple example, but in complicate and complex example, like imagine you want to design a tall building, 150 different floors, and you have an obstacle in each floor. Then how do you want to solve this permutation? How do you want to solve that each floor? How? And you want to look allocate the elevator. So how do you want to tell the algorithm which area is where he should go, which area where it should search, and which area is forbidden? It is really really get difficult and get a lot of time for you to define which area, where area, what should I delete, what should I allow. So instead of going for these complicated solutions, the best is to monitor what's happening and to find a constraint and define that constraint as a penalty. One of course, our treats is to define as a penalty. Let's see how can I solve this one. This is a super simple one. So I see that when my table goes here, let's get back to this. When my table goes here that I don't want, one thing that happened is that these lines have collision with this obstacle. Yeah, they have intersections. So let me tell my algorithm that if any of these lines have intersection with this obstacle, this is not a good solution for me. This is not what I want. So go for the next one. How can I tell them? One of the very very casual ways of defining a penalty function is to see if our optimization problem is a maximization or minimization. Mine is a minimization. So I will define the penalty function like this. First, figure out if it has any collusion. So is it the way of breaking collusion? Oh no, collusion. Am I right? Still not. Where is it? Still, I have some problem with spelling here. Let
I
me
think it's COLI.
still. SION, this one, yeah. So close, but not exactly. Still no. Hmm. Let me see in here. Training Grasshopper. Which one is the... Not yet, huh? What am I missing here? Okay.
As far as I know, it was point in curve or something like that. Maybe you can find it under curves.
I'm not exactly looking for pointing curves. I'm looking for collusion or curve collusion, point collusion, something like that.
It
But let
was
me...
yeah, that was the
Yeah,
one I used. When I was trying to solve, I went in a similar approach. It was
yeah,
like it worked that way when it was inside, when the point was inside of the boundaries of the curve. It was returning true and false.
yeah, yeah. I remember. Yeah. But I'm still looking for collusion. Collusion
It's
maybe
available
here.
in the intersection tab. Yeah,
Yeah,
this
here.
one.
So it was double L. That was the problem. Of course, it's because I have lots of plugins. I should consider deleting some of them because when you write something, it's difficult to find it. Yeah, this is collusion. Collusion one many. That was what I was looking for. Yes, COLLI. That's just what I missed. Now, now that I have collusion from this curve to my obstacle, where's my obstacle here? See what is the output? It will output some booleans, yes? False, 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 true, false. You know that we can convert booleans to numbers, yeah? So let's go to see from here. And now we just have some numbers. 0, 0, 0, 1. And you know 0 means false, 1 means true. What about I use a sum here? And now again, see the result here. So this is 1. So if any of our curves has any collusion, any interaction with the obstacle, what happened, what it result is 1 because, or at least more than 0. If we have 2 collusion, let's see what happened. Let me bring it here for a while. And yes, we have 2. We can have 3. Can we go for 3? Let's try. If I can handle this for 3. Yes, here we can see 3. So whenever it is more than 0 or whenever it is not 0, it means that we have a collusion, we have a contract, we have a intersection with the obstacle. Each of one of these lines at least has intersection. And whenever it is totally 0, yeah, it means that we are in a safe area. So how can I use this one? Let me see. I will add a if clause to this one. So the penalty means you want to punish the algorithm. Yeah, it's one of the main rules for training an algorithm. So the punishment is that if the result of this collusion is more than 0, then the solution should be so big that the fitness should be so big that the algorithms do not consider that as a good solution because our optimization is a minimization algorithm, minimization optimization, and our algorithm, our plugin, is searching for the minimum distance. Yes. So I do not let the algorithm to choose this one by mislead the algorithm. by trick the algorithm. Let's see how we can do this. We can say if, let me write my if here. So I want to set if x is equal to 0, then return y, which is my fitness. Else, add some very huge number to the fitness and then return that. So this is what is going to control, and this is my fitness. See what happened. So, and let me put the panel here as well. Here, the distance is 395 something, and because the occlusion is 0 here, the result is exactly the same, yeah? No, something is not. It doesn't understand this as a number. Okay, here, where is this one? And this one is the x. Yes, exactly. So it just a mislead parameter. So I change the parameter to the number so it can do the evaluation here. Now, when the collision is 0, you see that the distance is 395 something, and the result of my penalty function is exactly the same because the collision is 0. What happened is the collision is not 0. You see that what happened. It will add the 1000 to my result. So this solution's fitness is very big. And while the algorithm is set to minimize, it will not choose this solution as a good solution for us. So it will omit it, just lose this solution, do not survive. Do you remember about our first story of survival, the fittest are survive? Because this is too big, it will not survive. And what happened? It will go to search for another solutions, and another solution. You see how it changed. We have 1000, and here we have 3 digits. Here we have 4 digits. And I see some of the solutions that sent to me try to optimize using null solutions. It says that like if it was more than 0, or if we have more than 0 collision or more than 0 intersection, make the solution null here, or 0 and 1, or you just input the true and false result directly to the fitness function. Let me tell you what happens if you give the null solution to understand that the null solution or defining some null solutions is not a good way for dealing with algorithms, especially for optimization algorithms. You see what happened when you give a null solutions? Here, if you remember how our algorithm works was that like generation number 1, genome number 0. This is our first genome. It will evaluate it. It is our first parent. Will evaluate the fitness function of this parent, and the result is 242. Next one evaluated, and the result of fitness is 334. What if it evaluate the genome number 2 and the fitness function will be null? What happened? After that, it evaluates all the solutions fitness function. If you remember, when we evaluate all the solutions, all the parents fitness function, and then inbreeding child and evaluate all the child's fitness function, it will put all of these evaluation to a sort function and try to figure out which one is bigger, which one is smaller. And then when it is in a minimization, it will get the smaller one and forward them to the next generation. How it can compare a null solution with the other numbers? How our algorithm can understand if the null solution is bigger or 242, is the null solution is smaller or 337. Of course, there are some functions that try to avoid null solution or try to find a way to compare null solutions. Like in Galapagos, if the result of the fitness of any solutions is null, it will get back to the solution and make a mutation on that. In other language, it will change the solution, mutate the solution, and try to evaluate it again and do that as much as it needed. So while there is a lot of chance that your algorithm crash, there are some chances that it can just pass the null solutions and found a way to handle that. But the problem is that it's like you just let the algorithm to choose the solutions for you. You know, the more you let the algorithm to interfere in the optimization process, the less control you will have on your optimization process. So fitting a null solution to any procedure algorithm, especially optimization algorithms, is not a good idea. So if you want to have a control on your optimization process, control on your data management, the best way is to give a constraint, or one of the constraints is a penalty function. And this is the way I define it. You can define it in many other ways. But this is the simplest things that I can understand, I can figure out. And when I set the output, when I see the output, I will figure out if there is a problem because I know that how I train my algorithm, how I tell the algorithm to avoid the bad solutions or the solutions that I don't want. Now let's run the algorithm, run the optimization with this function. And as you know, the fitness of the Galapagos and of course the Wallisey and of course the biomorph or anything rather than the octopus, that you cannot input a panel, you cannot input anything rather than a number to them. So if I want to input this one as my fitness function, I should make it a number. Now, this is my fitness and the same, these are my genomes. Let's keep the window here and run the optimization. Let me run save. Okay, this toolbar is coming down now. This is a minimization problem. I want to just make it very small, or better to put this here so we can visualize what's happening. And minimization, don't want to change anything more. Just make sure that the evolutionary solver has been chosen. And okay. Oh, you should not run okay. Like every time I do that, you should set start solver. Nothing is okay. It's starting the solver. Yeah, here, start solver. And there we go. You see? This is what it found. And it's so similar to the optimal one that it found before because we put the obstacle in a very good way. This is it. So this is how we can define a constraint optimization algorithm by defining a penalty function to avoid the solutions that we don't want to reach. Now, let's move forward to more advanced optimization, which was a form optimization, yes? I'm waiting for the file to be open. And there we go. Yes, today we are going to use Giraffe too. But for now, let's disable everything here and let's go for our algorithm. So you remember our previous optimization form, yeah? Something happened to my Rhino, and when I minimize it, it just got freeze, and I should go for a restart. That was really weird and frustrated because it happened just before like 5 minutes ago. And I'm happy that it doesn't happen. So I just try avoid minimizing my Rhino in any way. And let me make sure that we don't have these either. And yes, that's all we want to do. So So you remember about our form here? We were discussing this in the beginning that how do you define your problem? And one of the participants said a good thing about it. It said that I should care about how I define my problem, especially in the terms of defining form or how my geometry evolve to avoid this kind of collusion, to avoid this kind of losing variation. That's true. And the bad news is that's exactly what we need to do on our own because the algorithm just know the number. Now, the other thing that you can do when the form variation is important for you is to define which form is your favorite or which form evolution, which form transformation is exactly what you want. It is similar to the penalty function. You said the penalty function, we said we should avoid, we should learn the algorithm, which solutions to avoid. Here, we should learn or train the algorithm, we should teach the algorithm which solutions we want more. So in this term, imagine that I want to design a building. I want to optimize the structure, or this is a tall building and the structure and stability is important for me. So in this case, whether I can change my algorithm, because I can change these dimension and constrain my dimension based on what I want, or I can just keep it this way. Maybe we have multiple optimization. We have like optimization of the tall buildings structure, and it's like isovist, it's view or a structure and daylighting because like this one maybe it's better in daylighting because it had some more shadow, I guess. And or maybe this is a city we are going to have an urban optimization and the footprint should be minimal, but as a structural stability the footprint should be maximum. So when we have some contrasticity between our objectives and we want to go for multi-objective optimization, maybe we cannot constrain our form generation here. So what I can do is to add some quality, some special geometry form from my form generation to the objectives, because the only thing that the algorithm consider for generation different solution is the number, is digits, is the so what I can do is that like I can make the area of, if this is my top circle, yes, I can make the area of my top circle one of the objectives. This is the ground. Okay, we're going to speak about it later. So where is the panel? This is the area of my top circle, yes? So Michelle, so it will be top circle area. It's too long, so let's make it top circle area. Yeah. Then I'm going to input my top circle area as an objective. Area, yes. So top circle area. So this is the total area, this is the top circle area. I want to minimize these two. This way, I will make sure that the algorithm will converge to the forms that I favor more, or the structural stability affects my optimization convergence more than other things. So we will have some forms like this, but most of the forms, especially in the last generations, will be look like the other way, this way, because this is the way that I can affect the optimization convergence. This is the way that I can affect how the algorithm will evolve and choose solutions for me. And of course, this is the only way that we can affect that in the policy and the other components like that. We later we see in biomorpher we have other controlling But in Policy or any other just coding algorithm, this is the only thing that we can do. Now, let's go further, run this optimization and see how we can get out the data and see other data. We go through these the previous day and yes. So let's keep the generation size 20, the generation count 10, and start optimization. Here you can see that we have three fitness objectives. Fitness objective 1 is volume, fitness objective 2 is area, and fitness objective 3 is top circle area. And you can see that this time, because we have three objectives, our Pareto front chart is 3D. The z-axis is the fitness objective 3 added to the two fitness objectives we had previously. And here you can see that a new chart has been added to our charts because this chart, this diamond chart, can be only generated when you have more than two fitnesses. Let's see how this chart is working. So if I go like the previous session and select something here, let's select the fitness objective 1. And the best solution based on fitness objective 1 is rank 0. Let me select this one, which is this. Now let's see this diagram. This diagram shows us that the solution that has the best result in the fitness objective 1 has the worst result in fitness objective 2 and near to worst result to the fitness objective 3. What about the other one? 2 rank 0, select. This shows us that the solution that has the worst result in fitness object 1 actually acts good in fitness objective 2 and 3. Now we can guess what, because these two, fitness objective 2 and 3, they are both calculating area. So it is obvious that they are related to each other. And this is what we expect, that fitness object 1 is totally have contrastivity with 2 and 3 because it was the volume. This is the total area and this is partial area because this is the area of the circle. So in the in some way you think that this is nonsense because both of them are area, and why should I add a partial area when I have a total area? This is because of the form. This is for the sake of your form generation. This is because I want to control the algorithm and train it to set which form I favor more. That's the only reason we add this one. Otherwise, just having the volume and the total area would be enough for this for this type of particular example that we have. Great. Go further. You can see here too. You see in the parallel coordinate plot, we can see that fitness objective 1 has contrastivity with objective 2 because when in this fitness in this solution, when the objective 2 is minimum, if I continue this line, you see that the objective 1 is close to maximum. But here, objective 2 and 3, they have so similarity, a little contrastivity that you can see here, but so much similarity in compared to this one with the other one. So let's show all here, or we didn't run any clustering net. And there is other controlled charts that you can control and manage the output data. One of the very famous one is the unsupervised machine learning algorithm K-mean clustering that we have here. This will do clustering. This is a kind of classification, but not in the but not exactly classification. It's kind of classification. It is different because classification is based on having a same attribute. You mean all of the solutions in one classification means that this solution has at least one same attributes. But clustering means that is based on similarity. So it is kind of different. We're not going to go through this because it's kind of advanced and you need to know a little about machine learning algorithms. But just for having a concept, this is kind of classification. So let's see how it can classify our output. It asked me the generation to cluster. I said the final generation and number of cluster. Let's go for 3 and see if it can do this. No, it can't. What happened? What about the 2? Yes, 3 was too much for it. So this is how it cluster. And why it is favored with the all computational designer and also with other scientists rather than classification, because in clustering, because it's based on similarity and it will calculate similarity based on some mathematical function, you have something called the center of cluster. The center of cluster can represent the whole cluster in the terms of similarity. So instead of seeing each of the solutions in this cluster, if we just output the phenotype, the form of the solution in the center of cluster, it is so similar to the other forms of the other solution in this cluster. So we can see here in this window, we can see that we have the center of cluster. This is the center of our first cluster, and this is the center of our second cluster. These are, this can be a good representative of the whole solution in each cluster. So we can add these two to the export list here, and then export them. Let's do this. I should input phenotype, or I have inputted previously. Yeah, this is our phenotype. We have input that. Now we can go for the export. It says that you choose 2 and I say yes. Yes. Let's get back here. These are our phenotypes. So as we said previously, we have 2 ways to decode the phenotype and see both of them here. You see these 2. Let me make sure that these are only our output and nothing else are previewed. These 2. Or it's better to go to distributed to the grid. Oh, sorry. So as you see in the distributed to the grid, we need to input fitness, we need to input phenotype, and it distributed it very easily. And also carry some additional information about it. Let's make the text size a little bigger. Okay, now I need to make them. I'm just trying to control some visualization here. Here. So as it says that if we divide the whole solution of the last generation, I choose the last generation, generation number 9. You see both of them are from generation number 1. If I want to cluster the last generation individuals, the last generation solution, it can be clustered to 2 different groups. And these forms can represent these 2 different groups. So as you see, the final generation, which should give us the best solutions because it is the final generation, it represents that most of the forms, one half of the forms I can say look like this. Of course, it's not exactly one half, but in 2 clusters, one of them is look like this, like 5, 10, 12 of them look like this, and the rest are look like this. So I reach what I want. You see that the algorithm generating forms similar to what I want rather than those different forms. So that's I think that's it with the Wallacey analytical. We are going to go more analysis with giraffe, but before that, I want to show you that Wallacey has a lot of analytical component that you can find it in its folder. When you download the Wallacey, if you open the Wallacey, here you see the example file, and in the example file in Wallacey analytical, you see here. And if you can open this file, Hopefully nothing bad happened. I'm really not sure what happened to my Rhino in those hours, but something had happened. Well, it can't open. Let's try again or for the last time. Yes. So this is the file, and these are the analytics that you will get. These are the bar and charts and diagrams that you can output from the Policy. Now we are trying to replicate something similar to this with Giraffe and discuss which one is how each of them work and which one is maybe more favorite for you. And yes, you can have found this file when you download Policy. Now let's go forward and see how we can get out some data from that. Okay, let me take some steps back because this is a objective optimization. I just copy these three objective optimization here and turn it to two objective optimization. See, this is our previous objective. This is our previous optimization problem. And this is what we're going to do. So again, we get back here. We have a cylindrical shape. Yes. And we have the volume and area to minimize. We have the phenotype. And we run the optimization. Let's run it one more to make sure that everything is okay. Yes, two objectives. Yes, it looks like it is correct. And there we go. We have everything here. Let's get back here and see what I'm going to do. First, for be able to manage the data that Policy output, we need to know how the data structure is working with Policy. Let me see if I can delete everything here and start over all of them. Yeah. Yeah. So the Policy output, the optimization data in a way of tree. You see, if you work with Grasshopper, you know what is data tree. Hopefully I can find prompt viewer. Yes, there it is. You see, so it output the data in a data tree manner. And what does it mean? In any of these lists, the first number means the generation, and the second number is the solution. Here, as I write here. So this is generation number 0, solution number 1, generation number 0, solution number 2. And how many generation we had? I guess 10. So from 0 to 9. So the last number that you see is 9. And in each generation, how many population we had? I guess 20. So here we'll go from 0, 0 until 0, 19 because it starts from 0. So 0 to 19. Yeah. So here we have generation, here we have solutions, and this is a data tree. As you may know, for for outputting a specific data from a data tree, we use tree branch, here. And there are multiple ways that we can do it. Like we can just type what we want. We can say a curly bracket, like 0 and 5. This is the branch that I need. There we go. So we will get 0, 5. Where is it? 0, 5. I output this branch and I have it here. What we have in each branch, as you can see in what we have in each branch is 2 items, and these 2 items are representing our fitness functions, because here we are outputting the fitness. Yes, this is our fitness values. So we have 10 generation. Each generation has 20 population, and each population, each solution we have has 2 fitnesses. One of them is volume and the other is area. Now, since we're working on a parametric design plugin, and we know that in Grasshopper, we want to do everything in a parametric manner, we can make it automated. So we can automate how we want to get output from the 3 branches. One of the easiest one to automate this one is to use format. Of course, you're always welcome to use Python or C Sharp, but then there is a ready component. Why should we do that? As you know, if you work with any coding language, in the format manner, I should write like something like 0. This is a function that make a placeholder for me. Let me see if I write it correctly, or maybe that's it. We will check. And 1 and another one. No, I need another one. Yes. One more curly bracket. Yes. That's the correct format. So these are the placeholders. 0 and 1 are placeholder. I can set what to put in 0 and what to put in 1 for me. Let's see, what was this one? 0, 5. So 0 here and 5 here. Now let's take a look at the output. Is exactly the same thing that we want. So if we input this to our 3 branch, and we get the exact same result that we had here. Why is it good? Because we can just change it parametrically this way. So this is generation number 0, and these are all my solutions from 0 to 19. Yes, from 0 to 19. The good things that you can do with this, with Wallacey, is that you can make an animation with them. Let's see how we can do that. Did we output any form? Let's output the whole generation. Yeah. Let's here go to generation. And I said, yes, I want to see the whole generation's phenotype, the whole generation's form. Sport, 200. Done. Thank you. Back here. Now, the same that I output the fitnesses, I can output the phenotypes, this time from here. Or if I want to see the phenotypes, first I should decode. Yeah, I should decode the phenotype. And then come here and see the whole geometry. Yeah? What is wrong? Oh, because this is totally different. Okay. Let's first go for this one. Yeah, this is my genotype, and then decode it here. There we go. And let me preview off what we see here, and this is it. Now, what do you think about making animation like this? So this is generation number 0, and these are my phenotypes. You see? And this is my final phenotype, final solutions in all generations. Oh, because it is too much. I have only 10 generation from 0 to 9. Yes. You know that if I come here, right click and say for animate, it can just go and save each of these changing as a slide, and you can make a GIF out of it. You also can use a text tag here and write something here that's like generation number 1, and you can you can output these ones. You say these are fitnesses. You can just write down the fitnesses here in the in the Rhino preview, and that's the way. Now, what I want to do with Giraffe is to get more information about how my optimization goes through the data, how it digests, and how I can just explore more or dig in what I have from my outputs. If you remember that we said that Wallacey can draw the Pareto front here. You remember this chart that we had there? Now, let me try to make this chart and then make the similar one in Giraffe and then compare these together. So first, I need to use Wallace Analytical here, give the fitness values to this one, and get it from here. And this is my chart. And also this one, if we want to go for more things to see. Okay, let's go to the top view. This is it. So this is Wallacey Pareto front, the only Pareto front that you can output from Wallacey. But what was my problem with that? That we had the idea of writing and plugin like Giraffe. It did not give us any values. Like here, if I want to see what are the fitness of this particular solution, this solution or this solution, there is no digits, values, or numbers here. This is because it's just made like a 3D surface and some points. You see, this is just generated as a geometry generated here. These are not the exact plot or chart or numerical analysis. These are mostly for visualization. Yes? But what if I want to know, like, what is this, what is the fitness of this particular solution? How can I output these solutions for myself? Because in this Pareto front, I see these are so maximum for this fitness. So maybe these are my favorite solutions. I want to see the phenotype of these solutions. I want to see how these solutions generate form and what are their fitness and other sort of things. For this, you can go to Giraffe. Not this one, not this G, looking for another G. Yeah, Giraffe, scatter plot. So with Giraffe scatter plot, you just need to input some points and see it's a scatter. So since we had fitness values for all of the generation, and as you can see here, the first one is the volume and the second one is the area, I can output the fitnesses like this. Not like this, like this. And there we go. Now let's make these are flatten, flatten, and flatten. Now let's take a look at that. These are all of my volumes in the whole optimization process. Yes, if you remember, we had how many phenotypes we have? 200. 200 volume fitness and 200 area fitnesses. Here we can see. Yeah. So now that I have my volumes and my areas for all of the solutions in the whole optimization, let's make a point from that. Let's output this to the point, and that's all we need. Get back to the giraffe, not this G. Okay, hopefully this one, yes. Now what I need is a plot, is a view, and some properties. I also need a bitmap to preview. And I guess that's it. Yes. So after inputs my points to the specific plots that I want, we just go for plottable and then the bitmap. There we go. See what we have here. The whole generation scatter plot as the the similar thing that we had here, you see? But what we have more is here we have numbers, you see? I know this solution. This is the amount of volume and this is the amount of area. I can exactly dig in and interact with all of my solutions. Let me add more.
Aquí solo. ¿Más se siente?
Sorry, your microphone is open. Okay, thank you. Now let me add a little properties to be more clear. I want to say which one is volume and which one is, want to add label, volume in the X and area for the Y. Yeah, there we go. Now, what if, oh, okay, I can replicate. Now, what if I told you that I want to select solutions that their areas are less than 350 and their volumes are less than this number? You see? I'm trying to dig in more. I want these ones. I want to see these solutions. You can do this with Giraffe and of course the data management output that you learn here. You know that how to work with format now and how to exactly get these data's output. How we're going to do that? Let's see. First, we need to define and function to filter the output of our fitness functions in the volume and in the area to maintain between 350, I mean 0 to 350 and 0 to this number. You can do it very easily with Grasshopper, you know, that we have something called call index, call number, call pattern. Then we can set to, these are our volume. These are our fitnesses. Let me make it more clear this way. Volume and area. This is better. Now we know what we are doing. So I want to my volume to be less than what? 0.00025, yes? Was that the correct number? 0.3025, yes. And my area to be less than 350. Yes. Now let's call the whole numbering. Let's call the whole data based on this pattern. I will go for this one, minimum or equal, or less than or equal. Less than or equal from this, less than or equal from this. Actually, this is not correct because we want to be both. We want to we want to have those items that has the both condition, less than this and less than that. So I should add an AND gate. Yes, less than similar to this, less than similar to that. This is correct. And let me see. That's true. So I need to add an and because I want to do both condition to be true. So and this one and this one. So these are the fitness 1, these are the fitness 2. Let me make another scatter here and map the second scatter to the first one with a different color. So now that I have my specific fitnesses, the fitnesses that I want to see, let's input this to the scatter plot. Let me move everything here a bit further. Put this one here, put this one here, and this is my plotty. And as you know, we need to flatten. There we go. This is what we were looking for, yeah? Less than 250, less than this weird number. You see how simple you can work with this dear plugin, Giraffe? These are the way that we did that before with all of the group that we work on this plugin. This is what we discussed previously. We discussed that we need some data management plugins in Grasshopper that just care about data directly and give us information, not just visualization. We need to, instead of just saving our files in Excel or outputting everything in CSV, go to Python, go to MATLAB, and try to dig in more in our data and try to draw some charts and plots. We need to do that exactly in Grasshopper because Grasshopper has a very good potential for this type of data managing. You see, we have everything I need here. We just don't need every time to go to encode all of these components that we have. We can reach easily here. So what if I tell you that I want to see the phenotype of these two? So now I know where I am. I know which solutions I'm thinking about, I'm working on. How I can get out the phenotypes, get out the forms that representing these solutions. The same as we did here. You see, we have the pattern we want. And also here, we have all of the forms. Yeah, we have phenotypes here. So let me output the phenotypes. These are my phenotypes. Output them. It says that, oh, okay, it's because I need to flatten that. Output 35, you see this is 35, the list length is 35, and I have 35 phenotype for these fitnesses. Now, let me use decode. Where was the decoding phenotype item? Here. The only problem that we have is that decoding the phenotype do not show the phenotype one by one. I mean, it does not distribute the phenotypes for us. Why give us just one? I input 35 phenotypes. I get only one output here, a closed brep. Okay, let's decode that here first. Let's see if that works. Then I have a geometry. Turn it off. Yeah, it works this way. I don't know, these are small bugs of policy or something wrong with my computer, but it worked this way, not really differently. Now, let me take this preview off, everything off, even this one. And now we cannot use the distributed to the grid anymore now, but we are Grasshopper. We are very good in Grasshopper. We are master of Grasshopper, and we can write distributed to the grids on our own. This is the way that I write it. Let's just copy and paste it here to go a little faster so we had time to talk about biomorpher as well. And enable. And let's see, what are these? I cannot guess. And disconnect them all. Don't need this one. Okay. You know that we have grid here. not grid structure. Oh my God, too much confusion here because I had too much things here. Yeah, this one. This is what I'm looking for. This is a grid plane. And how many phenotypes I have? 35. So 7 multiplied by 5, yes? This is how much grid I need. 7 multiplied by 5. Is it enough, you think? Is it?
Oh, no.
Yeah. I'm sorry, again, your microphone is on. And I'm going to make it a big one. Yes, now we can see that. This is my grid. What I'm going to do is just to draw a bounding box around my phenotypes here. If you know how we are going to map all of these forms to the main of the grid. This is the center points. Let me make it flatten. And 35. Let's see. If we have 35, where's our geometry? This is it. There we go. So simple, so easy, and so fast. We can make our own grid to visualize our phenotype. Now let me give them the same color we have here. I want to add a swatch here. This is the color of things that here I want to see, and I will going to put it here. That's it. You also can add more tags, you can add some tags, and I think I have it again here, hopefully, if I did not change anything. Yes, here. Ouch. Let me add some text tag to write the fitnesses, so similar to what they do in the policy. Which one is this one, I guess? Okay. Mhm. Something is going wrong here. Okay, I think then we can go to that example. That example is almost ready and just need to be enabled. Yeah. And here's something. Yeah. Because we did not add the phenotype yet. This is it. Okay, I'm going to clear the file and share it later. Here I added text tags for area. So now you have all of your phenotypes, you have all of the text tags that writes beside of this, and it is so similar to distributed to the grid that already had in the policy. But this is the way that I just want to told you how you can dig in more in the data and how you can not just visualize, but really understand the amount of each data, the numbering, anything you need to know about what you have here. We had more here. I had add more plots from Giraffe. You can see this is a similar example that I try to solve there. This is just what I do in the morning. You see here, this is less than 300 and less than this one. Let me input this one. This is how we want to see this one. This is a very specific one. I'm going to explain this one A2. and also this one. Yes. One of the specific things that I did here, I said I just want to visualize like the data from generation number 5, and this should be from 0 to 19. If you want to just visualize a specific data and a specific solution here, you just need to name it here. You see which solution? Here, this, let's change the solution color in a very dramatic way. And let's go for this. Like, is it clear how it changed? Should I bring it here? Zoom more. And you say how dynamically and fast it changed. Like you can choose this one and go to your form and annotate that this one is something that I'm talking about and write something next to it. This was another use of giraffe. And also I go for more plots. I go for bar plots. I want to say, okay, if this one, the area, these are the solutions that I want to work about, how about have a visualization of how their fitness are changed here? You see? These are the exact solutions. I make a bar plot from them, from their fitnesses. This is the volume. And this time, as you remember, we, for minimization, because we want to maximize the volume, we go for 1 over x, 1 over volume for minimization. This time I go vice versa because I want to see the exact number because I can do it now. I want to go 1 over x, 1 over volume, and these are the exact amount of my volume. So for this particular data, for this specific data, I made a pie chart. I made 2 bar charts, one of them for area, one of them for volume. And I made a heat map. Heat map input needed a data tree. What I did again, I export some data. What are these data? This one is, as you can guess, this on generation number 0. And as you see, instead of said which solution I want, I said I want all solutions. Let's see this here. So as you remember, we could say like, I want generation number 0, solution number 5 with using format. Yes? Now, instead of said that which solution you want one by one, you can input a series. So generation number 0, solutions number 0 up to 19. This is another way of getting output. Now, what it will output of is this 0, 0, 0, 1, 0, 2, whole solutions of generation number 0. So actually it goes for 18, so I go for 20 here. And this is all. This is how you can output the whole generation in once. This is what we did here. So I output the whole generation here and try to plot a heat map. Heat map will show me how the amount of numbers are changed in each generation based on color coding. Because if I want to say like in this 0 generation number 0, it's generation number 5 and this generation number 9. If I just want to take a look at the numbers, you see these are the fitness values of volume for generation number 0. If you want to read all of them, compare all of them together, it will be a user fatigue. Have you heard about user fatigue? Like when you want to go to buy a sunglass, you try one sunglass and then try second one and compare the first one with the second one and you can decide. With the third one, the first one, the second one, the third one, still you can decide. But when you go for 10, for 12, for 20, in that case, you said that I cannot decide anymore because I don't remember how the first one looked like on my face. This is called user fatigue. It happens when we have multiple of choice, plenty of choices, and we can't go comparing all of them because our mind do not keep the whole informations for multiple choices. So when we want to compare data with each other, we cannot just go and see, okay, this one 394, so we have a variation, or no, this generation does not have high volume as much as I want. This is difficult to do in our mind with numbers. But with color coding, it will be super easy. Here, I can tell you generation number 0 has the most variation. You see, we have many colors here. So we have many different variation in the volume, because it's volume. Am I right? Is this volume? Yeah, this is volume, because here I say 1 over, and yeah, I put 1 overs to this one. So this one is volume and this one is area. So I can say that, okay, there are lots of variations here in the generation number 0. And when we go to generation number 9, I see that there are very contrasted here. You see a very dark color with a light color, where a light color represent the higher numbers and the dark color represent the lower numbers. So I can see that in generation number 9, we have variation, but the variation is much more like contrasty. We have very high volumes and very small volumes. While in generation number 0, as you can see, that contrasty is not really considerable. So this is how we can use heat map. Now, putting all these plots together, we can dig in how many uh, other plots you can do, and you can dig in more on your outputs, on your data, and on your optimization problem. We can just correlate each of these outputs data with their forms. You can visualize them in the Grasshopper, in the Rhino canvas, and this is not only visualization, because you know the exact value of the fitnesses of each of these forms. The more value you can add, the better understanding and analysis you will have. You can add the height of these towers to your data, and then you can just color code them based on their heights. You can add like the top area to these data. Instead of 2 axes, you can have 3 axes, because in Giraffe we have 3D scatters here. This is a 3D scatter. So you can go for a 3D scatter, you can go for a 3D surface, and you can have the your Pareto front, 3D Pareto front here with a 3D surface. These are all of the things that you can do with Giraffe, and we are really waiting and looking forward for your feedbacks. That you use Giraffe, do you like it? Does it help you? Do you face any problem? I see that in the group, someone mentioned that they face some problem in installation. We in the morning, I think, our colleagues sent some instruction for installing the Matplotlib library and to solve that problem. So if you go and work with Giraffe, please give us your feedback. We will release the Giraffe like tonight or the other day, but soon these days. And on Food for Rhino, I will send a notice in to group to confirm that we have uploaded in the Giraffe in the Food for Rhino, and we'll appreciate any feedback or any bug reporting or anything you think about the Giraffe. So let me get back to see if there is any question and everything is obvious to you. Any question? Okay, you have my voice. Yes, I'm not disconnected because I do not get any feedback.
Yeah, we can hear. I just couldn't
Yeah.
think of any question yet.
Yeah. That's great. Thank you, Fatima. Thank you. Thank you, Fatima. Thank you for your feedback. I hope everyone enjoyed that. So let's have a 5-10 minutes rest. And when we'll back, we will go through a 10-15 minutes introduction to biomorpher, because it is a totally different optimization plugin. This is a cluster-oriented optimization plugin, the cluster-oriented optimization algorithm. Yeah, this is a bit different, or I can say a huge difference with the other plugins that we have in Grasshopper. We'll go through a quick uh, introduction of the biomorpher, and then we'll wait to hear from you. We want to see if you had defined your own optimization problem, whether you have any question or you need any help for defining your problems, and to see what you do for our final project for the till the next week. So let's have 5 minutes rest, and we will back by biomorpher and also your feedbacks. Thank you.